All right, we're good to go. So, start with any questions.
Can you confirm the last homework problem?
Mm-hmm.
I feel like that one took the least amount of steps, but I feel like it should have taken a lot more steps than I took.
What was the last question?
That was if A divides X and A divides Y, then A divides 5X minus 3Y.
Yeah, that one is a little bit easier than the ones before it, actually, or a little more direct.
I just kind of said if X is congruent to Y mod A, then 3X is congruent to, or excuse me, 5X congruent to 3Y mod A. And I think I took a couple steps on that one, but a couple more than that.
Okay, let me see something. Let me hop onto Canvas. Let's see, homework 4. So I actually wanted those to be done using the proof techniques that we had discussed, with stating the hypotheses and then listing the reasons why each step is true and so on and so forth. You can do that with modular arithmetic also, but it's a different kind of proof. Same thing with the even odd proofs. You can do those by working modulo too. But
those ones I went through each step. I think it was the last one I just went through and was like, well, I'll use modular arithmetic and see how that works out.
Yeah, and that does make it easier, actually. Homework 4 hurt my brain a lot. Yeah, I can relate to that, and it is tricky with proofs to know kind of like, is this, a valid proof? Is this written the right way, and so on. That's why we do so many of them in here, because it's really kind of a trial and error thing to get to that.
I'm still really confused on number 1. I know we were supposed to prove the fallacy of denying the hypothesis and affirming the conclusion.
Mm-hmm.
I actually wound up at one point using the justification of conditional logic. So, for example, if the hypothesis is incorrect, that still means the conclusion can be correct or not correct. This is why that is a fallacy, right?
Yeah,
so conditional logic would be a good justification for solving that, right?
Right. So the idea here was to do something a little bit simpler than that, actually, which is just pick propositions P and Q which demonstrate these fallacies. So for example, let P be the proposition. It rained.
I probably way overdid it.
Let Q be the proposition, the grass is wet. So P implies Q is true, right? In a normal environment around Vancouver, if it rains, the grass is going to be wet. Now, if you have a canopy or something, right? But just think of like, an open grassy area on campus or something. P implies Q. If P, then Q. If it rained, then the grass is wet. Okay? So this is a true proposition. And suppose it does not rain. Right? Suppose it did not rain. This fallacy would say, therefore, the grass is not wet. and that does not follow logically, because maybe it didn't rain, but somebody went out with a garden hose and watered the grass, right? So knowing that this is true and this is true does not let us conclude this statement, right? Because it could be true that if it rains, the grass is wet, and it could be true that it did not rain, but yet, the grass might be wet because someone watered it. So that's just an example of specific propositions P and Q for which it's pretty easy to argue that, these two things can be true, but this might not be true. And so denying the hypothesis is not logically sound. And the other version, affirming the conclusion, is this: if it rains, the grass is wet. The grass is wet, therefore it must have rained. That's not logical. It could be that it didn't rain, but somebody watered the grass with a garden hose. So these two things do not lead you to this thing, right? That's a fallacy. It could be that P is true. It could be that it also rained, and that's why the grass was wet. But it could be that it didn't rain, but the grass is still wet. So that's what those are, is sort of picking your own versions of P and Q, and further convincing yourself that, this does not follow from those, this does not follow from those, that kind of thing. All right, go ahead and do an attendance note. Please let me know you're here. And so let's take a look at homework 5. So homework 5 is a half dozen number theory questions. Is there a way to show that mathematically? Number 1. First tried and then failed. What was number 1? So can you tell me a little further what you mean by, is there a way to show that mathematically, number 1? You mean using like mathematical propositions? Well, send me a clarification of that question and I'll see if I can answer it. Alright, so homework 5 is number theory related stuff. So 6 questions. First one is playing around with modular arithmetic. So just tell me what each of these numbers is congruent to in these moduli, right? And remember, if we're working mod 8, your answer should be between 0 and 7. If we're working mod 11, your answer should be between 0 and 9. So that's what this bold-faced note is. If you're working mod n, make sure your answer is between 0 and n minus 1. Because technically, I could write 26 as the answer, and that would be correct. 26 is congruent to 26. That's not the answer I'm looking for. So I want to know what it's congruent to, what the number is between 0 and the moduli minus 1. And so play around with these. The first few you can just do by, dividing and seeing the remainder. When you have a negative number, right, it's a little trickier to get your answer between 0 and n minus 1, but think about it, mess with it, right? And then these last two don't take a lot of work if you think about them the right way. So that's playing around with some modular arithmetic. Question 2, which of the following numbers are prime and which are composite? And if they are composite, list at least one factor of the number other than itself and 1. So that's kind of a trial and error thing. Question 3, write the following numbers as products of powers of primes. For example, 25 is 5 squared. Oh, I gave you the answer to one question. But do that for these other ones, right? So this is playing with that fundamental theorem, writing these things as a product of primes. Fourth one lets you practice Euclid's algorithm. So there's some pairs of integers. Use Euclid's algorithm to find the greatest common divisor of 10 and 15, or of 1066 and 572, or of 1260 and 45, and so on.
This is going to be on the midterm next week, right?
This is fair game for the midterm, yes.
Okay.
And then questions 5 and 6 are doing exponentiation using these tricks of modular arithmetic. So question 5 use modular exponentiation. So in other words, calculate 2 to the first, 2 squared, 2 to the fourth, 2 to the 8th, 16th, 32nd, and 64th, and then combine those to get 2 to the 130th. And then question 6, this was something we ended with last class, which is Fermat's little theorem. So a to the p minus 1 is congruent to 1 mod p. So set p equal to 7 and see if you can find something about, 2 to the 6th being congruent to 1 to get you an easy way to calculate 2 to the 6,002. So go back and look at the notes if you're not sure. So write those up, show all of your work. Please don't just put down, these you can just put down an answer if you want. But for these calculations, make sure you show all of your work. If you just give me a number and there's no work, I have no way of knowing that you understand modular exponentiation or Fermat's little theorem. So show your work. All right, clear on that?
I know 2 to 6,002 power mod 7. We're not actually calculating 2 to 6,002. We're just calculating mod 7 of that number.
Sorry, say that one more time.
So we're not looking for 2 to 6,002. It's 8 bajillion and 500.
No. That's
that mod 7 is some number that's between it's 1, 2, 3, 4, 5, or 6.
Yes.
1, 2, 3, 4, 5, or 6.
Yeah, that's the whole point of these is to not do 2 times itself 6,000 times, but to use either modular exponentiation or Fermat's little theorem to do 5 or 6 calculations and then you get your answer. So it's this way to shortcut these large exponents.
But that doesn't tell us what that number actually is. It just tells us something about it.
It doesn't tell us what 2 to the 6,002 is. It tells us what the remainder is when you divide this big thing by 7. So there's information loss. Homework for number 2. Let me hold off on that one until Friday because there's a bunch of homework 4s that are still outstanding. And I'll probably grade one of those questions between 2 and 5. But ask again on Friday and we can go over any and all of the questions on homework 4. All right, so let me make some initial comments on the midterm. The midterm is still a week and a half away, but I want you to start thinking about how you're going to do the midterm. So the midterm will be 12:30 till 2 o'clock a week from Friday. Okay, it's on Canvas, and the format of the midterm.
Wednesday.
Sorry. Oh yeah, it's Wednesday. You're right. Yeah, it's a week from today. That's right, because Friday I've got programming assignments coming in. All right, so this is a good time to talk about the midterm. So the midterm is October 27th, and when it opens up, this will be a PDF file that you download. Okay, and it will have a bunch of questions on it. It will look like homework questions, for example. To submit your midterm, you need to write up the answers and then upload it as a PDF file. So the same thing you've been doing for homework, right? But, it's an exam, it's only an hour and a half, it's going to have a lot of questions. So make really certain of 2 things. One, that you have a way to do a nice, crisp, clean, easy to read upload of however you create your answer sheet. And 2, that you can do that efficiently, that it doesn't take you 15 minutes to scan or convert format or email something to yourself or things like that. Figure out ahead of time how to do this really efficiently so that it takes, maybe 45 seconds to do this upload. And if you're not sure how to do that, come by office hours, this week or early next week, and let's see what your setup is, what tools you have available, and figure out a good way for you to do this upload. So yeah, it's definitely not in person because everything is remote for this class, for this quarter. So it will be an item in this area of Canvas that will be available at 12:30 next Wednesday, and you download it, do the questions, and there'll be a place to upload your answers as a PDF file.
Is this going to be a lot of like homework style questions, or?
It's going to be exactly homework style questions.
Okay.
Not the exact same questions though, because there wouldn't be much point in that. But yeah, it's going to look like a homework set that covers multiple topics.
Okay. Do you know about how many questions?
I don't. I got to sit down and think about it. I'm planning to give you an hour and a half to do it, which is the full class time, and I'm probably going to try to target it to take about an hour and leave 30 minutes for a miscalculation on my part and so on. And I'm not going to give you a lot of proof questions because proofs take a long time. I might give you, a lot of questions where, here's two sets, show me what the union is or the intersection, because those don't take as long, right? So I'll try to balance it out in some reasonable way. And it will cover basically everything that we've done in the course up through and including this latest homework set that we just talked about today, homework 5. So those questions on modular exponentiation and modular equivalence and things like that. We're going to start talking about like crypto today. That will not be part of the exam. So we'll leave that for the final.
Okay.
Using your phone to scan answers that you're writing up is not a bad approach. With the caveat of make sure the scan is absolutely perfectly readable. And if you're doing this in a hurry and you turn in a fuzzy image or an image that's too light or too dark to read, that can affect being able to grade your answers fairly. So make sure that you're getting a nice, crisp, easy to read scan, and make sure that if you've got several pages of answers, that doesn't get in the way with file size limits if you're mailing this or something like that. So just do a practice run, and just try to scan several pages worth of answers and make sure you can get them into a PDF.
Do you want them on binder paper or blank paper?
Your choice.
Okay.
Me on the 215 midterm with shaky hands.
Yeah, right. Yeah, so there's lots of technology out there for this, and if you can take pictures and get JPEGs or PNGs, right? Certainly anything like Word or OpenOffice Writer or anything like that, you can just drag and drop those into a document and then just print it out as a PDF, export it as a PDF, and that should work. Or Google Docs or whatever. But make sure you've done this before, right? Make sure. I mean, you can practice with homework 5 if you want. You can upload something there and say, ignore this. This isn't homework 5 yet. But use that to upload something, pull it back down, make sure it doesn't eat your images and stuff. It's nice to work on a nice sheet of paper with a good soft pencil and a nice eraser, so that you can actually erase, because you probably don't have time to work out your answers and then write them up neatly. You might want to actually turn in what you're working on. But good erasable pencil marks are valuable.
If it helps anyone as far as the scanning thing, there's an app called Simple Scanner, and you can take multiple pictures and email it to yourself as a PDF.
Oh,
already.
cool.
I did that for calculus, and that was very nice.
Awesome. Thank you. If
Box is going too.
Say again?
Google Drive has one too.
Okay,
It's pretty
cool. If you really like producing documents electronically, using LaTeX or Word or something else, right, you can do that, but please don't let it slow you down. Right? So at this point, we've got lots of funny symbols, and propositional logic has all kinds of weird symbols, the little hooked horizontal bar, and we need to lay things out in a very specific way, and so on and so forth. Do not compromise the format just to try to do it electronically. Right? If you can't make it look the way that it's supposed to look electronically, don't do it electronically. Figure out how to write it and turn it into a PDF. And like I say, come by office and we'll figure out the best approach together if you like. All right, so that's a week from today, 12:30 to 2 o'clock. If you have an extended time allowance, you'll be able to just keep working on it and turn it in by whatever your extended deadline is. There will not be a closing time for this. It will accept late submissions, but late submissions get docked 10 points per minute, so you really don't want to turn it in even 1 minute late. You want to make sure it's in before Canvas considers it late. But if something happens and you get it in 30 seconds late, it's not an automatic 0, right? You just lose 10 points. All right, let's see. Let's talk about crypto. So you can take entire courses in cryptography. There's crypto courses offered, at the university level. I took a crypto course once through a math department, and that was interesting. And we're not doing that level of discussion in this part of the course, right? We're going to spend today and maybe a bit of Friday talking about this. But the idea is, part of what all this number theory is so exciting about is that it's, kind of the backbone of crypto systems. And cryptography is a big part of computer science, because, everything is connected, everything is networked, and you want to be able to share information from point to point, and you want to do that securely. And e-commerce, logging into the Linux server, pushing files over to Git, all the stuff that we do requires information to be sent securely. And one of the things to keep in mind about computers is that there's almost no physical security when you send bits across from one computer to another, right? You're going through, maybe a cable, but most likely you're going through the air. You're sending wireless signals, and anybody with a receiver can pick those up, right? Encryption does not stop somebody from receiving a signal. It stops them from understanding what they've received. And this is sort of the eternal story of cryptography. If you're trying to send a message to somebody in another town, how do you do it securely? Well, you could, get your strongest warrior and take your message and put it inside some, strong metal box and hand it to her, and she rides across town, and if somebody tries to get the message, they use their sword and they kill them, right? And you can try to physically secure the information. But in today's world with electronic communication, there is no physical security. There's no strong box or mighty enough warrior to be able to send information from one point to another and guarantee that nobody can look at it. And we can get closer, if you do fiber optic, it's a little harder to intercept without knowing that somebody cut the line and so on. But we really don't want to rely on physical security, on keeping somebody from looking at what you're sending. Partially because, when I log into a Linux machine from here, or I log into Clark's website, I have no idea where the keystrokes that I'm typing are actually going. Now, I know where they're ending up, right? They're ending up in the email server at Clark. But how do they get there? I have no idea. They go from my computer through a wire, which goes into a router, which goes into a modem, which goes into a coax cable, which goes into the wall. And I can trace that to a spot on the side of the house, and it connects to another cable, and I don't know what happens after that. But you know, at some point it probably turns into a wireless signal and gets transmitted somewhere. I don't know where it goes. I don't know where the cable is physically run. I don't know if in the middle of the night somebody cut that cable, put a splitter inside, and is now sniffing the traffic going through that line. So cryptography is the idea of, let's not try to physically stop somebody from seeing this information. Let's disguise the information so they don't know what they're looking at. And so that's sort of the underlying principle of all of these crypto systems. And people have been doing this for, you know, thousands of years. And so one of the earliest ciphers is something called a Caesar cipher. And this is also called a shift cipher. And the idea is trivial. If you want to send a message, you know, HELLO, well, you just add something to each letter. So I could just add one to each letter, and I could say, I'm going to send the message hello. What I'm really going to send is IFMMP. And if somebody intercepts my courier and steals the parchment, and they see this on it, they're not going to know what the message is. Right? Now that's the idea. And if you're the first person to have come up with this idea, that's pretty secure. Right? Somebody looking at this, they're going to be like, if and p, I don't know what that means. So this is one approach. And the person you're sending this to, if you've coordinated with them, they know how to decode this. What they do is they subtract one from each letter, and I becomes H, F becomes E, M's become L, and P becomes O, and they can read the message. Oh, hello. So this is plain text. This is ciphertext. And the process of going from here to here, this is what we call encryption. To turn this back into plain text, that's the process of decryption. And this is encrypted, this is decrypted. So we can make this a little more secure by, instead of just adding one, we could add some other number. So we could say we're going to add 3 to this. So our hello, our H is going to change into a K, our E is going to change into an H, our L is going to change into an O, and our O is going to change into an R. And now somebody intercepts this message and they try to subtract one from each letter, and they still get gibberish. And they can't read what this message says unless they know how to decrypt it. And so the encryption key here is +3. And the decryption key is, guess what, -3. And so someone mentioned Roth13 in chat. So Roth13 was the same idea, except you encrypt by adding 13. So A becomes N, and B becomes O, and so on and so forth. And then to decrypt, you could also subtract 13, right? But if you number your letters, you know, from 0 to 25, and you roll over if you add 13 and your number is too big, it turns out that, you know, subtracting 13 is the same as adding 13. And so Roth13 is a system that basically works mod 26. And to encrypt, take your letter, which is numbered from 0 to 25, add 13 to it, reduce mod 26. The normal decryption would be to subtract 13, but guess what? Minus 13 is the same thing as positive 13 mod 26. So ROT 13 is nice because you don't need a separate algorithm for decrypting. You can use the same process you use to encrypt to decrypt.
Wouldn't that make it very easy to decrypt it?
Yeah. So
Like
this
if you're trying to use it to secure classified documents or something?
probably not a good idea.
Okay.
So this was mostly, when Usenet was a thing and you might be reading bulletin boards at work and there might be words that you didn't want other people to see, so you could download it as a ROT 13 and things wouldn't jump out at you, but then it was easy to decode. But yeah, no security here, right? And so somebody pointed out, it seems like the biggest issue at this stage is information leaks about the key. And this is the glaring weak spot, right? You got to keep this thing private. And with a shift cipher, there's only 26 possible shifts, right? Assuming there's 26 letters, so you can brute force it. And I could subtract 1 and 2 and 3 and 4 and so on, and most of the time I'm going to get gibberish. But one of those 26 things that I'm going to subtract is going to give me words that I recognize. And then I know what the key is. I've cracked the password.
Well, you could literally write a function, right, to take in a string and basically add 1 to each, and then 2, and then all the way up to 26 and give you 26 individual print statements, right?
Mm-hmm, absolutely. That would be a cool program to do.
It would be.
It seems like, this could be a bad form of encryption, but as long as somebody doesn't know the keys, would it still be easy to figure this out if you were to go with like a +3, -3 encryption decryption or something?
If you don't know that it's a shift cipher, it might be hard to figure out. But once you understand that it's a shift cipher, it's pretty easy to figure out what the amount of the shift is. And this brings up.
Code breakers should break that in about 10 seconds.
Yeah. Unless it was too simple for them. So if you take Q to encrypt 11, so yeah, if you get past Z, you just roll back over and start over at A again. And that's why we can think of this as just a system that's operated mod 26. And same thing when you subtract, if you end up with something smaller than 0, roll it back over to something between 0 and 25. So there's two lessons here. The first lesson is that you kind of have to assume that people know what your encryption algorithm is. There's too much information on the web. It's too easy to reverse engineer computer code. If you have, a program that takes an input string and adds some offset to it to produce ciphertext, you got to assume that if anybody can access that program, they can figure out what the algorithm is. And the secrecy is really in the key value itself, not in the algorithm. So that's the first thing, right? You've got to assume people know what the algorithm is, and security comes from their not knowing what the key is. Which means you better have a really big key space, because if your only possible keys are from 0 to 25, you can brute force that, in no time. But if we took blocks of characters to form integers between 0 and 2 billion, and then we added some random amount to that, some key between 0 and 2 billion, that's a little harder to brute force. 2 billion is actually really easy to do, but we could take a chunk of characters and string them together into a 64-bit number, right? And we could have a ridiculous number of possible keys. At what point does the algorithm no longer become a shift cipher? So if you convert it to ASCII and then used multiplication, is that no longer a shift cipher? Probably not. But that would be a version of what we're going to talk about next, which is a replacement cipher. So with shift ciphers, right, you can brute force. But even if you can't brute force, you can attack this a variety of ways. So a really common, really simple way to attack some of these ciphers is to use a frequency attack. And so if you know that the message that's been encrypted was written in English, you can find tables that tell you how frequently different letters occur in English. For example, the letter E is the most common letter. And there's a frequency for how often it occurs in an arbitrary set of text. Now for a particular sentence, those frequencies may not be exact. But if you had, hundreds of pages of text, the number of times the letter E occurs, or the letter Q, or the letter Z, or the letter T, is pretty standard, right? It's pretty stable. And so one way to deal with a Caesar cipher is, if you have a lot of encrypted text, just look for the letter that occurs most often. And if you find that the letter G occurs more often than any other letter, you can make a hypothesis. Hey, G might correspond to the letter E. Well, how would you get from E to G? I would add 2, so maybe 2 is the encryption key. So now try subtracting 2 and see if you get your plain text out. So that's a pretty easy way to go about this. So a slightly different version of this would be a replacement cipher. And it's similar, except that So a shift cipher replaces each letter with another letter, but there's an algorithm for that replacement. So a pure replacement cipher might do something like this. It might say, the letter A is going to go to a Q, the letter B is going to go to a W, the letter C is going to go to a D, the letter D is going to go to A, and so on. And the letter Z is going to go to P, maybe. And unless you have this map, this guide of how you're encrypting, right, you get gibberish out the other side. And there's no simple way to decrypt that gibberish. You can't just subtract 3 from each letter. You have to know, if I see the letter P, that's a Z. If I see the letter Q, that's an A. So you need this guide to be able to decrypt. But again, you can do analysis. Right, whatever letter occurs most commonly, that's probably the letter E. So if we looked at our text and we saw F was most common, hey, that's probably the letter E. And you can find, frequency tables for all the letters and how often they occur. But you can also find combinations of letters. So in English, TH is a really common occurrence. And TH occurs a lot more than DB, for example. And so we can do a frequency analysis on the ciphertext and say, how many times do we see each combination of letters? And if we find the most common pair of letters is TH, for example, then whatever we find is the most common pair of letters in our ciphertext, we could say, hey, maybe that first letter is T, the second one is H. And so you can break these down pretty easily. All right, so that's a replacement cipher, and that's good for your diary at home maybe, but not for state secrets.
So you would rather avoid a shift cipher for a replacement cipher?
Not necessarily. I mean, shift ciphers are nice because they're so easy to implement, right? They don't take a lot of code, and if you're explaining this to your kid or a child or friend or something, it's really easy to work with. So that's a nice advantage, right? And it lets you do things like make decoder rings, right? where you can, you know, maybe adjust something in the bottom to say what the shift is, and then turn this dial around and see what the corresponding letter is. So breakfast cereals used to be able to get decoder rings inside, and that's just a shift cipher. But replacement cipher in general is probably a little more secure, but seriously, there's effectively no security, right? It's really, you know, you're passing messages to someone in your treehouse, and if the message falls down, you don't want your parents to pick it up and say, "What do you mean we're gonna, you know, rent some movies?" So, or bad handwriting works too. All right, so so there's other versions of ciphers like this. So we can do a permutation cipher. And you know, this is a secret. And so simple permutation cipher, well, you define some sort of block size. So let's say we're going to go in blocks of 4. So we'll break this into, you know, this space is space, A space, SE, CRET. That worked out well. And a permutation is just a reordering of things. We're going to spend a week talking about permutations later. But here's an example of a permutation. I could rearrange 1, 2, 3, 4 to be, I don't know, 2, 4, 1, 3. And so this is, it's a mathematical thing, a permutation. This is saying 1 changes into 2, 2 to 4, 3 to 1, 4 to 3. And so how do we use this to encrypt this? Well, this says in each block of 4, we should take the first letter and move that to the second position. We should take the second letter and move that to the 4th position. Take the third letter, move that to the first, and take the 4th letter and move that to the 3rd. And we do that in each block of 4 characters. So the space goes into the middle, the I goes into the end, the S goes in the beginning, and the space there goes into the middle. And so again, you get a message that looks jumbled up. And so that can work, but that's also pretty easy to crack. And to decrypt it, right, you need to know what this is, and if you know that this is the mapping, then how do you decrypt? Well, you just reverse it. So 1 is going to go to 3. So this is encryption, and for decryption, I'm going to take 1 to 3, I'm going to take 2 to 1, I'm going to take 3 to 4, and I'm going to take 4 to 2. So I'm just writing these arrows down in the reverse direction, and I reordered these. So to decrypt, the first character goes to the 3rd position, the second character goes to the 1st position, the 3rd character goes to the 4th position, and the 4th character goes to the 2nd. And there's your decrypted text again. But not super secure. Again, if we look at pairs of letters like TH, right? TH will get transformed into something where we'll have, you know, a T and an H, but they won't be next to each other. But they'll always be, you know, 2 apart or 3 apart or something like that. And we can search for those and start to break this down. And you know, it's a relatively simple mapping. So one problem with all of these is just the simplicity of the algorithm, right? And the simplicity tends to make it, you know, pretty easy to analyze the ciphertext and draw some conclusions. Another problem is the size of the key space. And, you know, a shift cipher, you've got 26 possible keys, and so on.
What about using random and seeds?
Like what?
Like, if these methods of encryption are somewhat easy to crack, or at least crackable, wouldn't it be a better idea to have some sort of random generation for an encryption and decryption, and then have that change a lot, so that even if you do figure out how to crack the encryption has already randomly changed?
Yes, so this is done sometimes. The trick is that when you do this, you still need a way to decrypt that's knowable by whoever you're trying to send the information to. So if it's purely random, you probably lose that ability. But for example, people have made codes where, you might have some kind of something fancier than a shift cipher, but something with a secret password that changes every day. And the password is, the fifth word on the front page of the New York Times, right? In whatever the lead story is. And you and your friend know that that's the secret password, but nobody else does. And so as long as you have access to this newspaper, you can figure out what the day's password is and decrypt the messages that your friend sent to you. So that's not random, but it's kind of like pseudo-random, right? It's a password, and it changes every day. So the Enigma machine that the Germans were using in World War II, their encryption keys had a 24-hour lifespan, and they changed every 24 hours. And the challenge was to not only figure out how to decrypt the messages, how to figure out what the encryption key was, but be able to do it in less than 24 hours. Because if it took you 5 days, by the time you figured it out, that password was long gone. So that can give you added security by changing the keys over time. But you still got to make sure it's really hard to decrypt the messages or figure out what the keys are for decrypting. And so that's a challenge. And so today we use algorithms that are much more complex. Yeah. I think that method is still used by various places, including in an episode of the Sherlock Holmes remake. And yeah, if Alan Turing invents the modern computer to do something, it's probably a tough subject. I agree with that. And this was where Turing machines came from, was trying to create a machine to do the kinds of things that were being done to crack these codes, for Enigma in particular. So one thing we can do for some security is we can make codes that are undecodable. We can come up with something where it's just not possible to decrypt. And so we can create these one-way encryptions. And they're algorithms that will take plain text and turn it into some kind of gibberish, but in a way that makes it more or less impossible to go from that gibberish back to the original. And so this is a one-way encryption function. Well, what good is a one-way encryption if you can't decode the message? This is how we store passwords. So you want to log into a system, and it says enter your password, and you type in your password, right? Baseball123. If that password is stored in a file on the machine you're logging into, you've got a security problem. Because there's a good chance that somebody will get access to that machine, or get access to a backup tape of that machine, or come in with a bulldozer and steal that machine. And once they do that, they have access to this file that says, hey, Nick's password is baseball123. And if that's my password on every system I use, I've been compromised now. So we never want to store passwords in a computer. So we run passwords through this one-way encryption algorithm, and we turn baseball 123 into something that just looks like junk, right? And then when you log in and it says, hey, what's your password? And I say baseball 123, what do? You run what I typed in through that same algorithm, and you see if you get the same junk. And if I type in anything other than my password, it will encrypt to something different from my stored encrypted password. But if I know the password, I'll type it in, it'll get encrypted to the same thing that's been stored. And now it can say, oh, you must be Nick, you knew the secret password. And now if somebody steals a backup tape that has, a copy of all the files on the system, and they go into the file called password, guess what? It doesn't say baseball 123, it says blah, 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 right? The encrypted version, and they can't reverse that because the algorithm used to encrypt my password was something that doesn't have a decryption algorithm. So that's one way to get around this issue of decrypting. But there's still times when we want to actually send a message and be able to get back to the original message, right? So for validating somebody, a one-way encryption is useful. But if you want to actually send some piece of information and have the receiving party turn it back into the original text, right? That's something that we still have to be able to do. And so a classic example is credit cards. If you're going to go online and buy something from Amazon, they say enter your credit card number, and you type in your number and you hit the enter key. What happens to that information that you typed? Well, if that just goes through your Wi-Fi router as a bunch of ASCII characters, you got a problem. Because anybody listening to the airwaves, right, and airwaves are public domain, anybody listening to the airwaves can get those ASCII characters and reverse engineer it, and they've got your credit card. And if your browser takes your credit card number and adds 3 to each digit and then sends that out through your Wi-Fi, somebody picking that up will take it and subtract 3 from each digit, and they've got your credit card number again. And if you encode this with a one-way algorithm, Amazon gets your encrypted credit card number, they have no way to decrypt it. They can't charge you for your purchase. So we want something where it's hard to decode what you've sent. And here's the other fundamental problem with all of these approaches, which is that all of these methods are what we call symmetric. Symmetric in the sense that in order to encrypt my message, I was told to add 3. Well, now I know how to decrypt messages, subtract 3. And if we're sending our information to Amazon, and I want to send it securely, and Amazon says, oh, add 3 to your message, right? Well, I can listen to your message going through, and I know all I got to do is subtract 3. And if you tell me, hey, when you want to send a message, here's what you do, rearrange your letters like this, well, anybody else who's using that same encryption key, I can decrypt their message. And the reason is, if I know how to encrypt, I know how to decrypt. If I know the first character is going to go in the second place, I know that what's in the second place is actually the first character. If I know that the letter H changed into the letter K, I know that when I see a K, that was the letter H. And so historically, all these forms of encryption, whether they're shift ciphers, replacement ciphers, permutation ciphers, all of this stuff, right? The way that you encode tells you how to decode. And that makes e-commerce really hard. Because with a symmetric cipher, Amazon would tell me, do this thing to encrypt your message. Well, if they tell me that, I know how to decrypt. And now I can look at other people's messages and decrypt them. So unless you can give each person their own encryption key, this is not secure. And Amazon does not want to have to talk to each one of us and tell us what our secret encryption key is, and find some way to give that key to us, because they can't send it in an email, because email is not secure. and they can't, you know, post it on our area of the Amazon site until we have a way to log in, and we can't log in until we know how to log in securely, right? So symmetric ciphers don't work for e-commerce or anything else, you know, online. What we want is a way for Amazon to say, hey, whoever you are, here's the algorithm for encrypting your information. And each person can take their information, encrypt it, and send it back. With the understanding / belief that this stuff that's being sent could be picked up by anybody. But only Amazon knows how to decode it. And that's the trick that makes this whole thing work. This idea that everybody knows how to encrypt, but only Amazon knows how to decrypt. Okay, think about that for a minute. All these other algorithms, knowing how to encrypt also tells you how to decrypt. The key to doing something like commerce over the internet is to have a way that everybody knows how to encrypt, but only one entity knows how to decrypt that. And that's tricky. But it turns out it's doable. And so this is something called an asymmetric cipher. And it's asymmetric because the encryption and decryption methods are related but distinct. You can't get one from the other. If you know how to code this stuff up, that doesn't tell you how to decode. And so Amazon keeps secret the decryption algorithm, and they make public the encryption. And so everybody knows how to encrypt, but unless you're Amazon, you don't know how to read that encrypted information. All right, so this is the notion of a asymmetric cipher, one with different encryption and decryption. And it's not the algorithm that's secret, but it's the password, right? It's the key. So you assume everybody knows what the encryption and decryption algorithms are, but there's a secret key. And knowing the encryption key does not tell you the decryption key. So this is not a new idea. Ralph Merkle, Martin Hellman, and Whitfield Diffie are the people who created this this algorithm. So the algorithm is a generated program that accepts an argument and only works with one single argument. So the algorithm is basically, I mean, you can have a program that basically you type in an encryption key and maybe give it a file name, and it will turn it into ciphertext. And then when you want to decode it, you run a different program, you give it the decryption key and the same file, and it'll turn it back into plain text. And the whole trick is that knowing the encryption key doesn't tell you what the decryption key is. There's no way to get the decryption key from the encryption. All right, let's do an attendance ping. We're at a good point of this right now. So some interesting history here. So this is 1960s, right? Long before, you know, an internet. I mean, computers were big room-size things and so on. you can see you know, a magnetic tape spool in the background here, and this is, you know, either an IBM or Honeywell or a PDP or some kind of old school machine, and usually no cathode ray tubes, right? Certainly no liquid crystal displays. Most of what was done on computers was done on paper, and you know, a teletypewriter that would move across and hit little pins on a ribbon and press ink against paper, and so, you know, they're staring at some output or some program that they're working on. So Merkle, Hellman, and Diffie. So some interesting history here. Martin Hellman was at Stanford, and he was interested in encryption, and he had this idea of an asymmetric cipher. This idea of somehow being able to save information in an encrypted form, but not be able to decrypt it simply by knowing how to encrypt it, right? And he was imagining, among other things, doing secure transactions electronically, right? This was like 60s, but he was picturing, how could we send information from one place to another that's encrypted, right, without somebody knowing how to decrypt, just by knowing the encryption key. So he was thinking about this, and he talked to some colleagues, and pretty much everybody he described this to had the same reaction, which is, that's impossible, right? You can't do that. Because pretty much every cipher that we had up to this point was symmetric. The decryption was based on how you encrypt. And so you know, when you have an idea and people tell you it's impossible, that's when you want to dig in and start going deeper. And if people get upset at your idea, you know you're onto something. I don't know if people got upset at his idea, but general idea. So he was interested in this. So that was Martin Hellman. Diffie had a bachelor's in mathematics, and sorry, I guess this was the 70s. He was walking around the country talking to crypto researchers, and he was just trying to learn more about cryptography, right? And he got to IBM and started talking to some people, and they mentioned Hellman to him, and they said, you know, this person's been talking out of Stanford about, you know, these weird ciphers. You should go talk to him, you know. So he contacted Hellman, and he made an appointment to come and visit for 30 minutes. He showed up sometime in the afternoon. They started talking. They talked until dinner time. They had dinner together. They kept talking. They finished like 11 p.m. that night. It was just like, you know, an instant kinship. And they were kind of on the same wavelength with, you know, how can we do this encryption, make it more secure, and so on and so forth. So they started working together on this. Around the same time, Ralph Merkle was an undergrad at Berkeley, computer science, and was taking a security class. And they had to come up with a project of their own choosing as kind of a term project for this course. And he thought it would be cool to try to do this asymmetric encryption, you know. So he came up with the idea, and he wrote it up, you know, like an SLP proposal, and turned it into his professor. And he thought it would be a cool project to work on for a quarter, right? And his professor said that his project proposal was, quote, terribly muddled, right? And didn't want him to work on this. He wanted him to pick something that was you know, closer to what they were doing in the course. So like any good undergrad student, right? He dropped the class so that he would have time to work on this on his own. So that was Merkle. So mid-70s, Merkle was working on his master's thesis at Berkeley, and he was talking to colleagues and so on, and somebody said, you know, there's a couple of guys at Stanford who talk just like you do. You should go talk to them. So he went over to Stanford, and he met Hellman and Diffie, and the three of them became colleagues, and they just started working on this stuff. So 1976, they had an algorithm for this asymmetric cipher. And Hellman published it in a journal. So, you know, when you do research, you take the body of literature, you understand what's going on, you try to extend it, and when you've got an extended result, you publish it. You put it in a paper, it goes out, other people look at it, they review it, and they either, you know, confirm what you've done, or they find problems with it, and this is how science is done. So he published this in a paper, and his colleagues got worried because they were starting to understand what this meant security-wise. And while it meant that you could send information securely without fear of it being decrypted, it also meant that people could have secrets that the government couldn't access. And up to this point, you know, the government had really smart people working for it. They had really big computers. They were in a great shape to basically be able to read other people's secrets. And this really threatened that. This was a way that theoretically, you know, anybody could take information, encrypt it, and send it in a way that would be almost impossible to decrypt. And so some of Hellman's colleagues contacted NSA, and NSA started looking into it and talking to their people about it. Anyway, they classified this algorithm as a munition, right? An instrument of war. It's like a gun. And they treated this accordingly from a legal standpoint. And they said, hey, if you go to a conference and you present this paper, that's and somebody in another country hears this presentation, that's like taking a gun and giving it to somebody in another country. And they said, we're going to treat it with the same set of laws, exporting instruments of war, things like that. And so the goal was to present this at a conference in 1977. There was a conference coming up. It would have been the perfect time. And, you know, to go on stage and tell people in the audience about this. And once you do that, right, the secret's out. Because once you describe an algorithm, anybody can use it. And so he talked to Stanford, and Stanford basically said, you know, if you're arrested and charged, we'll, you know, help fund your defense. We'll, you know, send people to court and so on. But if you're convicted, we can't go to jail for you, right? And we can't pay your fines. So Hellman, you know, he was tenured. He decided to take the chance. His two grad students, right, Diffie and Hellman, different situation. Because they were, you know, early in their career, they didn't have job security, that kind of stuff. But they wanted to go to this conference anyway, and they wanted to present their findings and their contributions to this research. And it was fairly tense, and nobody was really sure what was going to happen. Well, Hellman and Diffie talked to their families, and after talking to them, decided they didn't want to risk it. They decided to hang out on the side of stage Merkel and Diffie. And Hellman said, I'll do the presentation. So he went on the stage and he started talking, and people from the government were there, and nobody knew if there was going to be arrests and all this kind of stuff. And it turned out government let it happen. Nothing came of it. They gave their presentation, and from that point forward, this algorithm was public domain. And once the cat was out of the bag, everybody started expanding on this. And so RSA came around later that year out of MIT, and that's an algorithm that's still in use, and that's a one-way encryption algorithm. And it's been kind of a weird area for computer science. So I don't know how many people here, do you remember an old browser called Netscape? Anybody remember that?
I remember.
Yeah. You used to get CDs with it, you know. And there were two versions of Netscape. There was the version that you could use only in the US, which had strong encryption. And then there was the version that you could export and you could use in Canada or Mexico that had weaker encryption. And it was literally the size of the encryption key. 40 bits versus, I think, 128 bits or something like that. And the goal was to require that people who used this algorithm used a small enough set of possible keys that the government could still decrypt, right? Because the government wants to be able to read everything. And we don't have that anymore. I mean, we all use the same encryption algorithms, and we have strong encryption. We have, you know, stuff with 1,000 bits and so on and so forth. And you can pick your own encryption. You can use, you know, AES or Blowfish or whatever. But the government still wants to be able to you know, access information. So there's tons of conspiracy theories around all of this, of course. Speculation about backdoors in systems and secret, you know, decryption keys that only the government knows and things like that. The cool thing is all this stuff is open source. right? All these algorithms are public domain. You can study them, you can work with them, and the code that you use, you know, if you download a password vault and it's open source, you can inspect the code that's being used to encrypt your passwords, and you can figure out if there's a backdoor in there, if there's some master password that someone can use to read your secrets and so on and so forth. And the kind of open access mindset that we've been moving into is really beneficial for this in terms of security. It's weird, but in some sense, secrecy is kind of the enemy of security. Now, if it's your secret, secrecy is good, but if it's a secret how information is being stored or encrypted, right, that's a vulnerability. And this has been a huge mind shift in thinking in terms of companies and agencies and governments, right, to get to where we are now. And yeah, there are good stories of people who get nice job offers from some of this stuff. All right, so we have asymmetric ciphers now. And let's see, oh, we got about 7 minutes left. We can start talking about this. So we're going to work with one particular one-way algorithm or asymmetric algorithm, and we're going to do a really simplified version of this. And I actually have a video I posted that should be on the channel. If it's not, I can move it there. Where I go through and I take a simple message and actually do all of the steps from start to end. It's a lot of just watching somebody write numbers down on paper and use a calculator. So it's not terribly exciting or informational. But what I want to do is go through the algorithm at a high level, just to kind of let you have seen it once, and to let you see how the things that we've been doing in this unit with modular arithmetic and exponentiation and so on, how those things come into play to implement this algorithm. But the basic idea is built around primes, as we've said, and the idea that if you have two large primes, P and Q, and you multiply them, you can tell people what this product is. And have a pretty good security that even though you've told the world what these primes are when you multiply them, nobody can go back from n and figure out what P and Q are. And that's kind of the essence of the asymmetric security of this crypto system, right? So the idea is we're going to let people know what P times Q is, and we're going to hope they can't figure out what P and Q are. So if these are small numbers, you know, if I tell you that P times Q is 35, well, you know, you can factor that. It doesn't take long. You could write a program to do it, and you can say, oh, this is, you know, 5 times 7, so there's the two primes that you use. Well, you can crack my messages now. But if these primes have hundreds of digits, right, and you get this number n, which also has hundreds of digits, it's really hard exhaustively to factor that, right? A number with 100 digits is ridiculous. A number with 10 digits is 10 billion, right? If you can do something in a nanosecond, that's going to take you 10 seconds to do, assuming that you can do whatever the whole thing is you want to do in 1 nanosecond. When you get up to 20 digits, forget it, right? You're getting ridiculous. And so when these have hundreds of digits, right, with technology as we have it today, pretty hard to factor that into the two primes. But that's today. That's going to change at some point. And when that changes, everything that we're talking about here changes also, right? Because if you can take this 500-digit number and factor it into two primes with, you know, about 250 digits each, you can crack this this asymmetric encryption system. And I personally believe we will get there. I think it will probably come through quantum computing, but we're probably a good 20 years off. But that'll be a strange day. All right, so this is going to be the algorithm called RSA, and there's our three champions of the story, and I cannot pronounce their names. I should learn to do that. But it's Rivest, Shamir, and Edelman. I think I've got those pretty close. So MIT, 1977, and on the back of the blackboard here, there's a little P equals NP thrown in there. I don't know if that was a joke or not, but if you know anything about PNP, that's a cool little. All right, so those are the RS and A in the RSA algorithm. So let me just get you started on this, and we'll work it all out next time. So the first thing is, this works on blocks of text. So this is a secret. So we could break this into blocks of, say, 4 characters, or 4,000 characters, or something like that. Doesn't really matter, but the bigger the block, the more secure it's going to be. So we'll work with small blocks just for the sake of doing this on paper. And to further simplify this, we're going to assume that you're only working with uppercase letters A through Z. So I would actually write this message as, you know, this is a test. And you know, when you actually use this, you use the full ASCII set. In fact, you use sets of bytes, right, with one of 256 possible values. But for drawing pictures and working with this on paper, we're just going to simplify, assume you're just working with 26 letters, A through Z. And we're going to code each letter as a 2-digit number. So A, B, C, down to Z. This is going to be letter 0, 1, 2, and this is going to be letter 25. And we're going to write each of these numbers as a 2-digit number. So that'll be 0, 0, 0, 1, 0, 2, up to 25 for the letter Z. And this is just for the goal of changing your message into a bunch of digits. And these digits are going to represent really big numbers, right? And we're going to do modular things on them. So you're going to take your message and you're going to write down the 2-digit number corresponding to each letter, and you're just going to string those out side by side. And then we're going to break it into chunks. And we might break it into chunks of, you know, 500 digits, 500 digits, 500 digits. And RSA is going to encrypt each of those chunks independent of the other chunks. So we can think of this as something that basically takes a 500-digit number and changes it into another 500-digit number. That's the basic operation. And then to decrypt, we take that crypted up 500-digit number, we turn it back into the original one. So RSA is really about how do we take this number and change it into another number, and do it in a way that is asymmetric. And so we're going to have some message M, think big long integer, and we're going to have some encryption key, and when we apply that encryption key to M, we're going to get some new piece of ciphertext C. It's another big number. And the whole idea is that even knowing the key that was used to go from here to here, we don't know the key that we need to go from C back to M. But if we created this encryption key, we know what the decryption key is, and we can take this ciphertext, turn it back into plain text. So how does this work on the web? Effectively, Amazon tells your browser, hey, when you want to send me a credit card, use this to encrypt. The browser makes that encryption, sends the ciphertext. Somebody down the street in a van picks up that ciphertext. What's the credit card? I don't know. I don't have the decryption key. So my card is secure. Amazon gets that ciphertext. They know the decryption key. They can turn it back into the original text, get my credit card, complete my purchase. All right, that's the basic setup. So the whole mathematical side of it, which we'll do on Friday, is how do we encrypt this into ciphertext and how do we decrypt it? And how does knowing this encryption key not tell us what the decryption key is? And that's related to factoring products of primes, basically. All right, so we'll go through this pretty quickly on Friday. I'll rehash the basic setup, and I'll just show you the steps. And this is not, something I'm going to ask you to do on a test or on a homework, but it's something that I think is fun to have seen. What I do want you to know, and this won't be on the midterm, but for the final, I want you to understand the concept of a symmetric versus an asymmetric cipher. Right, that's the main takeaway from this that you might see on the final, is the idea of, does the encryption key tell you the decryption key, or are they independent of each other in some sense? But we'll go through an example of this. We'll see the math behind this on Friday, and that will do it for encryption. And then we're going to go back and talk more about proofs, and we're going to come back and learn sort of the one of the 2 or 3 central themes of this course, which is mathematical induction. So we'll finish up RSA encryption on Friday, and then we'll talk about induction. Please send me one more attendance ping, and we're technically got 2 minutes left. I'll let you out 2 minutes early. Have a good afternoon. I will see you next time.
Have a great day.
Thank you. You too.
Thank you. Take care. Thanks, everyone.
All right, you too.